Hello, this is one of a series of videos on the AQA A-level Chemistry Paper 3 or component 74053, specifically the 2018 paper. Here I'm going to be focusing on the multiple choice questions. When you are marking your answers when you've been through past exam papers, you'll find that the multiple choice questions will give you an answer, but it won't explain how to get there. So hopefully by watching the videos, watching the explanations, you'll understand a bit more about how to get to the correct answer. And when I've uploaded this onto YouTube, I will put timestamps in there so you can easily navigate to the questions that you want to find. Alternatively, you might want to just work your way through a paper 3 and then just pause as you get to each multiple choice question so you can understand how to get to the answer that way. So moving on to question 5 then. Which one of the following is both an empirical and a molecular formula of a stable compound? So A is the correct answer. I'll explain why in a second, but let's have a look through options B, C and D. So B, P4O10. Well, you should know that is the formula for phosphorus oxide from the period 3 oxides topic in second year. However, it is not an empirical formula. The empirical formula is the simplest whole number ratio, so the empirical formula would be P2O5, so that's an incorrect answer. NH2 is not a stable compound. Nitrogen will have formed 2 bonds with hydrogen. There'll be an unpaired electron in there, so that's probably going to exist as an ion instead. So that would not be the correct formula or molecular formula of a stable compound. CH3, you should know, carbon forms 4 bonds. So CH3 is a methyl group. It's often attached to something else, or it's got a lone electron or a free radical. So CH3 is not the molecular formula of a stable compound either. CH2O, like I said before, is the correct answer. So CH2O, so you've got 2 hydrogens bonded and an oxygen. Now oxygen should form 2 bonds, carbon should form 4 bonds to make it stable. So that is a stable molecule, and it is in fact methanol, which is often drawn like this instead. It's the simplest ratio as well. You've got 1 carbon, 2 hydrogens and an oxygen. So that's also the empirical formula as well as the molecular formula. Answer A is correct. Question 6. Which diagram shows the correct bonding and correct bond polarity in a molecule of oxygen difluoride, OF2? Fluorine forms 1 bond. Oxygen, in a stable compound, will form 2 bonds. So looking through these, if there's 2 bonds with fluorine and from oxygen and 1 bond from each of the fluorines, it won't need to be a dative covalent bond. So B and C are incorrect because these represent dative covalent or coordinate bonds. So it's just going to be 2 normal covalent bonds there. You should know that fluorine is the most electronegative element. It's more electronegative than oxygen. So fluorine draws the electrons towards itself. F is going to be delta negative, O is going to be delta positive. So F is delta negative, O is delta positive, 2 covalent bonds from the oxygen, 1 from each fluorine. Answer A is correct there. Now question 7 and question 8, they're both from the atomic structure topic and they're linked together. So it's to do with the experiment where they were working out atomic structure using helium particles or alpha particles fired at a gold sheet. And what they found, that most of the particles fired from the source of helium ions or alpha particles hit source P, despite there being a gold sheet in the way. Now the fact that these He2 plus ions were hitting source or detector P means that they must be passing through the gold sheet. Well, how could they pass through the gold sheet? And what conclusion can be drawn from this specific experiment? It contains electrons. Well, it does contain electrons, but you can't conclude that from this experiment. neither can you conclude that it contains protons or neutrons. That conclusion can't be made. But what you can conclude is that if most particles are hitting source P, there must be loads of empty space within that gold sheet. So answer D is correct there. The follow-up question, question 8, is that most of the particles did actually pass through the gold sheet and hit source P, as you saw in question 7. But 1 in 8,000 hit point Q. So there's a little detector up here that was detecting the helium particles. So you had your gold sheet and the particles were fired here, but some of them were reflecting off the gold sheet and hitting the detector up here. So what conclusion could be made about that? Well, the fact that alpha particles are positive, helium ions, alpha particles, means that something must be causing them to be reflected. And it is in fact that gold atoms have a small positive nucleus. It's not big, because if it was big then more than 1 in 8,000 would be being reflected. It must be positive, because if it was negative electrons it would be attracting the helium ions towards it, which it's not. So it must be a small positive nucleus, the rest of it being empty space, as we saw in question 7. Gold atoms have electrons in orbitals. You can't conclude anything about where the electrons exist, nor can you conclude about the sea of delocalized electrons, and you can't say anything about the number of protons in there. So answer A is correct. Question number 9. Which of these represents a termination step? So you first came across termination in the haloalkanes topic when you were looking at free radical substitution and the decomposition of ozone. Termination is where you have two free radicals reacting together to form one molecule. It's called termination because the reaction is terminated. The very reactive radicals can no longer react, as they are stabilized by forming a molecule. So you can quite easily glance through here, work out which one, if you know what termination is, which one has two radicals to make one molecule overall. So answer D is correct. This is the termination step in the decomposition of ozone by CFCs. Just go through the other ones just to show you where why they're not termination. So this is an alkane. This is answer A. Alkane plus a halogen radical will make an alkyl radical plus HBr. That's a propagation step in free radical substitution. B, you've got a ClO radical plus ozone to make a chlorine radical and 2O2. That's a propagation step in the decomposition of ozone. So you get your ClO radical from CFCs. And it's a chain reaction where lots of ozone will break down. Question C, you've got this RO radical. That comes from a peroxide. And the peroxide acts a little bit like a catalyst. The peroxide initiates the reaction in the formation of polymers, formation of addition polymers, specifically polyethene. So again, none of them are termination reactions apart from answer D. Question 10. Which statement is correct about the molecule shown? So it's quite a complicated molecule. We've got a lot going on here. You have a CBr bond, haloalkane. You have two carbon-carbon double bonds, and you have a C double bond OH, or an aldehyde. So these are three separate topics, lots of reactions, lots of knowledge is required to answer this question. So does it react with HBr? Well, HBr does react with alkenes. How do those reactions occur? It occurs in an electrophilic addition reaction. So not electrophilic substitution there. So that statement is incorrect. Statement B, it reacts with NaBH4 in a nucleophilic addition-elimination reaction. So the aldehyde, the CHO group, just on the right hand side of the molecule, will react with NaBH4. That's a reduction reaction. It occurs as the H- ion, the hydride ion, acts as a nucleophile and is added to the molecule. There is no elimination that occurs. So it does react with NaBH4, but that's in a nucleophilic addition reaction. So statement B is incorrect. Statement C, it reacts with ethanolic KOH in an elimination reaction. Now haloalkanes do react with hydroxide ions dissolved in ethanol via elimination. I'll just remind you how this mechanism works, because this is an answer that many students have given as the correct answer. So the hydroxide would usually attack the adjacent hydrogen. That will cause a double bond to form, and then the halogen breaks off. And you're left with an alkene and water. In this case, however, notice where the CBr bond is. There are two adjacent carbons. Neither of those carbons have a hydrogen bonded to it. So there is no adjacent hydrogen the hydroxide can bond to. So you would not get an alkene forming, you would not get elimination. That reaction would normally occur, but not in this specific example. And then finally, statement D, it reacts with KCN in a nucleophilic substitution reaction. So KCN, the cyanide ion, will attack a delta positive carbon, acts as a nucleophile, bonds to the carbon, and the bromine will break off in a nucleophilic substitution reaction. So that would happen. That statement D is correct. Question 11. Which statement is correct about 2-methyl-butan-1-ol and 2-methyl-butan-2-ol? So when it's given you two molecules here, it's worth drawing both of these out. So you've got 2-methyl-butan-1-ol. So your OH is on carbon 1, and you have a methyl group on carbon 2 there. 2-methyl-butan-2-ol, you're going to have a similar thing, methyl group on carbon 2, but also an OH on carbon 2. And your CH3 at the end. So A is correct, we'll come back to that in a second, but I'll go through the incorrect answers first. So can they both be oxidized by acidified potassium dichromate? Well, methyl-butan-1-ol can, because it is a primary alcohol. 2-methyl-butan-2-ol cannot, because it's a tertiary alcohol. You cannot oxidize this group because there's a methyl group there and two R groups either side. So that statement's incorrect. Can they be formed by the hydration of 2-methyl-but-2-ene? So if you've got your but-2-ene there, carbon 2 is going to have your CH3 there. So can you hydrate it to form butan-1-ol and butan-2-ol? So if it's hydrated, you're going to add a water molecule. You're going to add a water molecule onto either carbon 2 or carbon 3. So you could form butan-2-ol, but you could not form butan-1-ol, because you're not going to be able to get an OH group on either of the first carbons or either of the end carbons. So option C is incorrect, because you cannot form 2-methyl-butan-1-ol. Do they both have 4 peaks in their carbon NMR spectra? So how many carbon environments do they have? Methyl-butan-1-ol has 1 carbon environment, 2 carbon environments, 3, 4 and 5. So one of them will have 5 carbon environments. This one, the second one, will have 4 environments. 1, 2, 3, because both of the methyl groups are equivalent, and 4. But methyl-butan-1-ol will not have 4 peaks. Can they be formed by the alkaline hydrolysis of esters? So both of the alcohols, whatever the carboxylic acid is, if you hydrolyze an ester by acid or alkaline hydrolysis, you're going to get an alcohol formed. It can be any alcohol, and you're going to get, if it's alkaline hydrolysis, the carboxylic acid salt. But that's irrelevant to the question. Both can be formed by alkaline hydrolysis of esters. Question 12. Solutions of the two compounds W and X react together. Here's your balanced equation. That's got nothing to do with the rate equation, so we can ignore that. When all W, X and Y are doubled, the rate increases by a factor of 4. So what's a possible rate equation? So we're looking at the overall order here, really, to start off with. So if the rate was first order overall, I'm just going to choose A, B and C because it's irrelevant at this stage. If I doubled A, if I doubled one of my reactants, then the rate would also double. So it can't be first order because the rate wouldn't increase by a factor of 4. If it was second order overall, so for example if it was A squared or A times B, if I double the concentration of A squared, that increased by 2, then the rate would increase by 2 squared or 4. So if it was second order overall, if you double the concentrations, then the rate will increase by 4 times. So it must be a second order reaction overall. Just go through and just show you third order because answers A and B are third order overall. So if I was to double the concentration of W and double the concentration of X, the overall rate would be increased by a factor of 2 squared times 2, or a factor of 8. So it can't be third order because the rate wouldn't increase by a factor of 4. So A and B are incorrect. Has to be a second order reaction. So either C or D are correct. So second order, you double either X and Y or X and Z. D is incorrect because Z is a product. The concentration of products has no effect on the rate of reaction. So C is our correct answer there. Question 13. Here we're given a graph of concentration of reactant against the rate of reaction. Now, as the concentration increases, the rate would also increase if it's second order with respect to X. So conc and rate are proportional or proportional squared, so it cannot be A or B. So that's showing as concentration increases, rate decreases, which is incorrect. So it has to be C or D. Now if it was first order, that would be a linear graph because they're directly proportional. If it's second order, that's going to be like a half x squared graph. So concentration is proportional to the rate squared. So D is the correct answer here. Question 14. Which equation represents the process that occurs when the standard enthalpy of atomization of iodine is measured? So this is where you just have to learn the definitions. What is atomization? Well, atomization is where you're forming 1 mole of gaseous atoms from the element in its standard state. So iodine, we should know iodine is a solid, and if you're forming 1 mole of gaseous iodine atoms, you need to make sure it's balanced, so you need half I2 as a solid. So answer A is correct there. Question number 15. Which structure is formed by aspartic acid in a solution at pH 12? So when you were learning about amino acids, at a higher pH or in an alkaline environment, then what's going to happen is the COOH groups are going to become COO minus. Your NH2, your amine groups, interchange between NH3 plus. In an alkaline environment, there's an absence of H plus. alkaline environment, pH 12, you're going to have your COO minuses and you're going to have your NH2s. Because aspartic acid has two carboxylic acid groups, as we can see here, both of them would be COO minus. So answer D is correct in this case. Question number 16. How many peaks are there in the carbon-13 spectrum of 1,4-dimethylbenzene? So let's draw it out. You can either put your benzene ring in the middle, you can put your alternating double and single bonds. But because we're looking at carbon NMR, I'm going to draw in the carbons just so we can identify those peaks or those environments a little easier. CH3, CH3, and then these are your H's. So remember, in benzene each of the carbons forms 3 bonds as opposed to 4 because of the ring of delocalized electrons. So this molecule is symmetrical, so the two CH3 groups are in the same environment. So that's environment A. The two carbons attached to the CH3 or the methyl group, because it's symmetrical, are equivalent, they're in the same carbon environment, so that's our second environment. Now the CH groups, just circle one of them, each CH has a carbon with a methyl group next to it. It's got a carbon and hydrogen, and then a carbon with a methyl group 2 carbons away. Now again, because it's highly symmetrical, each of the CH groups has exactly the same surrounding atoms. So all 4 of the CH groups there are in the same environment. Let's call that environment C. So answer C is correct. There are 3 carbon environments, so there would be 3 peaks in the NMR spectrum. Question 17. Which of these period 3 elements has the highest melting point? So you learnt this in the periodicity topic in first year, and you also learnt it in second year when you looked at the period 3 oxides, so you will have revised it then. So you have your period 3 elements going from sodium across to argon, so sodium, magnesium, aluminium, silicon, and then sulfur, phosphorus, chlorine and argon. Which one's got the highest melting point? Well, it's not going to be sulfur, phosphorus, chlorine or argon. They're molecular or monatomic, so they're just going to have weak van der Waals forces between molecules or atoms in the case of argon. So is it going to be sodium, magnesium or aluminium, or is it going to be silicon? Sodium, magnesium and aluminium are metallic. They have strong attractions between delocalized electrons and positive metal ions, and silicon is macromolecular. Covalent bonds require more energy to break than metallic bonds, so silicon is the highest melting point in period 3, but that's not one of the answers. So which one of the metals? It would be aluminium, due to the fact it's got a higher charge density or a greater charge and a smaller ionic radius than the sodium ions. So aluminium would have the highest out of these options here. Question 18. Chlorine reacts with cold sodium hydroxide in a disproportionation reaction. Now when it reacts with sodium hydroxide, it's going to produce sodium chloride, it's going to produce sodium chlorate, NaClO, and it's going to produce water. NaCl, sodium chloride, NaClO is sodium chlorate. So which one produces sodium chloride, sodium chlorate and water? Well, it could be A or it could be C, because you've got 2 different sodium chlorates. This is just one of the reactions that you have to learn from the specification. What's the oxidation state of chlorine in sodium chlorate, NaClO? If Na is +1, oxygen is -2, That means the Cl must be +1. So answer A is correct. Just as a side note, if chlorine was to react with hot sodium hydroxide, you make the other option or the other products. So you get sodium chloride, sodium chlorate 5, and water instead. But cold NaOH is the one on the specification, that's the one that you have to learn. The one in hot NaOH is not on the specification. Question 19. Which of these products are formed when magnesium reacts with steam? So just like the previous question, this is a reaction that you need to learn from the specification, specifically from the Group 2 topic. You will have learnt the observations for this. You may have seen this done as a demonstration. So when magnesium reacts with gaseous water or steam, it produces a white powder, which is magnesium oxide. It burns with a bright white light, and it produces hydrogen gas as well. So magnesium oxide and hydrogen are produced. Not to be confused with A. So if you were to react a group 2 or group 1 metal with liquid water, you will get the metal hydroxide and hydrogen gas. But because it's steam in the question, you get a slightly different combination of products. Question 20. Which observation would confirm the ammonia gas is released when solid ammonium chloride is warmed with calcium hydroxide? So how can you test for NH3 gas? We should be aware that NH3, ammonia, is a base, i.e. it will accept protons. How can you test for a base? Well, all these answers refer to litmus paper. So red litmus paper in the presence of a base will turn blue, but it has to be damp litmus in order for the reaction to occur on the actual litmus. So it can't be blue litmus paper turns red, because that would be the observation for an acid. So that rules out answer A and C. So damp red litmus paper turns blue. It's going to be one of those when touched onto the solid mixture or when held just above the solid mixture. Now, because it's a gas, if the gas is produced, you want to hold the litmus paper just above it. If ammonia gas is present, the damp red litmus will turn blue. Now, we can't touch it onto the solid because calcium hydroxide is also a base and would also turn the litmus paper blue. So B is incorrect, D is correct. On to question 21. The repeating unit of a polymer is shown. And as we can see here, it's a condensation polymer, and it's specifically a polyamide. So we have a C double bond O and an NH there, which is that amide link, and you've also got a C double bond O and an NH at the end. Because we have two C double bond O's and we have two NH's, that suggests that this polyamide or condensation polymer is made up of a diamine, that's the two NH2 groups, and a dicarboxylic acid or a diacyl chloride. That's a C double bond O's, and again we've got two of those. So it's going to be a diacyl chloride or a dicarboxylic acid. To work out what the monomers are, again because we've got two of each functional group, we need a di of both of the functional groups. Next to the C double bond O's, we've got 4 CH2s. Next to the NH's, we've got 6 CH2s. So having a look through the options, it's not going to be A or B. So it has to be C or D. Which one has the correct monomers? You've got your 6 CH2s between the amine groups, and you've got your 4 CH2s between the diacyl chloride groups. So answer C is correct. Question 22. The structure of a polyester chain is shown. So in this polyester, what statement explains why plastics often soften at high temperatures? Sorry, only soften at high temperatures. Well, when you've got polymer chains, they're effectively really long molecules. So because they're really long molecules, what's happening at higher temperatures is that the intermolecular forces between the chains, that's what these dots are representing, are going to soften and break. So therefore we're looking at the intermolecular forces present between molecules or chains of this polymer at the top. So reading through the statements, C and D would not be correct. We're not breaking bonds in the chain. So therefore, is it hydrogen bonds and van der Waals forces, or dipole-dipole forces and van der Waals forces? So essentially this question is saying, what are the strongest intermolecular forces between the chain? Well, you've got your CH groups, you've got your benzene ring, that's going to provide van der Waals forces between the chains. You have your C double bond O single bond O. Now these don't have an OH group on them, so therefore it's not going to be hydrogen bonds. These are polar groups. If they're polar groups, it's going to be your dipole-dipole forces between chains. So answer B is correct. Question 23. The nitration of benzene uses a nitrating mixture of concentrated nitric acid and concentrated sulfuric acid. Which of these statements is correct? So in this equation we've got nitric acid acting as a base. Is it acting as a catalyst? Is it acting as an electrophile, or is it a reducing agent? So this specific equation, your sulfuric acid is donating a proton to become HSO4-. So because the sulfuric acid is donating a proton, that means it's acting as an acid. Your nitric acid, HNO3, is accepting a proton from sulfuric acid. This breaks down to form NO2 plus and H3O plus. So the nitric acid accepts a proton. The nitric acid is acting as a base. It's not a catalyst because it is the main reactant. It's used up in the reaction. So remember, your benzene reacts with nitric acid to form nitrobenzene and water. So it's a reactant, it's not a catalyst. The HNO3 itself is not an electrophile, it's the ion that's formed by the nitric acid that's the electrophile. So that statement's incorrect, and it's not acting as a reducing agent. Nothing changes in its oxidation state, there is no redox in this overall reaction. So again, A is correct here. The nitric acid, even though it's an acid, is acting as a base because the sulfuric acid is a stronger acid than nitric acid. Question 24. Aqueous solutions of ammonia, ethylamine and phenylamine are prepared. Which one has the highest pH, which one has the lowest pH? So this is from the amines topic when you're looking at the base strength. So if it's got an R group attached, if it's a primary, secondary or tertiary amine, these are often stronger bases because the lone pair on the N is more available to accept a proton. Phenylamine is a weaker base than ammonia. So the reason it's a weaker base is because the lone pair on the N gets partially delocalized into the ring of delocalized electrons. So the lone pair is less available to accept a hydrogen ion or to accept a proton. So this one is our strongest. Ethylamine is our most basic, which means it's going to have the highest pH. Phenylamine is our least basic. It's going to have the lowest of the pHs. NH3 is going to be in the middle. So ethylamine followed by ammonia followed by phenylamine. Answer C is correct here. Question 25. Which element forms an ionic oxide that reacts with strong alkalis? So this is from the periodicity topic in year 13. We have aluminium, magnesium, sodium and sulfur. So going across period 3, we have sodium followed by magnesium, aluminium in group 3, silicon, phosphorus, sulfur, chlorine and argon, but they're not on the specification. So they're oxides. Sodium and magnesium oxide are basic. Your non-metal oxides are acidic. And aluminium oxide is amphoteric. It will react as both an acid and a base. So which one is an ionic oxide that reacts with strong alkalis? Well, that rules out sodium oxide and magnesium oxide because they're basic. So they will react with acids, even though they're ionic. The acidic ones, silicon oxide, phosphorus oxide, sulfur oxides, will react with strong bases, but they're not ionic. These are covalent substances, with silicon oxide being macromolecular and phosphorus and sulfur oxide being molecular. So they're not ionic. Aluminium oxide mentioned was amphoteric. It also has ionic bonding. So it's amphoteric, which means it reacts with both acids and bases. The aluminium oxide is an ionic oxide that reacts with strong alkalis and strong acids. Aluminium is correct. Question 26. Which statement is correct about this reaction here? So we've got hexaamine cobalt. That's reacting with diethylamine. That's a bidentate ligand. So you've got 3 bidentate ligands being added, and we're getting this complex over here where you've got 3 bidentate ligands bonded. That's an abbreviation. And 6 ammonia is given off. So because it's a bidentate ligand, the coordination number stays the same. The coordination number is still 6 in both of the complexes, because there's still 6 coordinate bonds. The enthalpy change is large and positive. Delta H in this reaction is approximately 0 because you're breaking 6 cobalt to nitrogen coordinate bonds, and when the diethylamine bonds, you're making 6 cobalt to nitrogen coordinate bonds. So because you're breaking and making the same type of bonds, the enthalpy change is approximately 0. The entropy change is large and positive. That is a correct statement. I'll come back to that in a second. The shape of the complex changes from octahedral. So linking to answer A, there's still 6 bonds. If there's 6 bonds, the shape is going to remain as octahedral. So it's not changing. So answer C is correct. The reason it's correct is because you're going from 4 moles on the reactant side to 7 moles on the product side. There's a big increase in the number of moles, therefore the entropy change is very positive. Question 27. Which complex exists as optical isomers? So optical isomerism occurs when you have a 3 bidentate ligands. So it wouldn't occur in a linear complex. You wouldn't get optical isomerism when you have 2 of one ligand and 4 of another, but you would get geometric isomerism in this case. So you get cis-trans isomers of these complexes. So B, you would get optical isomers. I'll just very briefly draw these in here. So you have an octahedral complex with your bidentate ligands, and depending how those bidentate ligands are bonded depends which of the optical isomers it is. So for example, if your C double bondos, single bondos are bonded on the left hand side here, the optical isomer would be bonded something like this. And I'll just draw where the ligands go on the pair of enantiomers. So you do get optical isomerism if there are 3 bidentate ligands. This one is correct. Now EDTA, you aren't expected to be able to draw the structure. The exam board made a mistake here with this question because actually EDTA complexes will also form optical isomerism or optical isomers. That's not on the specification though, so the answer B is correct, even though the answer C is also correct. Question 28. How many structural isomers with the molecular formula C5H10O react with Tollens reagents? Now these questions usually take a while because you have to work out how many structural isomers there actually are. So how many of these will react with Tollens reagent? So if it reacts with Tollens, that means it must be an aldehyde, not a ketone. So how many aldehydes are there with the formula C5H10O? Well, the obvious one is going to be your pentanal, 5 carbons in a row. So that's 1. That's an aldehyde, it would react with Tollens. Then we're trying to make structural isomers, so we're going to have to keep the aldehyde group. So you could have 4 carbons in a row with the second carbon having a methyl group. So you're going to have 2 methyl butanal there. The methyl group could also be on the third carbon. So you could have 3 methyl butanal, which would react. And then finally, is there any other ways you could rearrange this? Well, you could in fact have 2 methyl groups on the middle carbon. One way of writing that formula there is the second carbon is going to have 2 methyl groups and your aldehyde at the end, dimethyl propanal. So that gives us 4 aldehydes that would react with Tollens reagent with that formula. Question 29. Which one would not catalyse the reaction between iodide and peroxydisulfate? So this is from the catalysis part of the transition metals topic. It also comes from the electrochemistry topic. So we've got peroxydisulfate in the first equation. That's a very positive value. Peroxydisulfate's on the left, so that is reduced. Our iodide is on the left of the equation. It's a more negative value than the ones above it. The iodide is oxidized to iodine. So in this case, our cobalt 3 plus and our cobalt 2 plus and our Fe3 plus and our Fe2 plus have values in the middle or between the values for iodide and peroxydisulfate. So the cobalt 2+, which is answer A, let's just go through how that works as a catalyst. The cobalt 2+ is more negative than the peroxydisulfate. So the cobalt 2+ would be oxidized to cobalt 3+. As the peroxydisulfate is more positive, it is reduced to sulfate. Once it's formed CO3+, so once the cobalt 2+ has reacted to form CO3+, the CO3+ would then be reduced back to CO2+, because that value is more positive than the iodide value. So the iodide would be oxidized to I2. So cobalt 2+ would act as a catalyst because it will cause the peroxydisulfate to be oxidized, and then it will return to its original state as it causes the iodide to be oxidized, and the peroxydisulfate is reduced. A similar thing happens with Fe3+ and Fe2+, because the value is between the two values for iodide and peroxydisulfate. So your Fe2+ would be oxidized to Fe3+. The peroxydisulfate is a more positive value, so that is reduced to sulfate. The Fe3+ that's formed, or the Fe3+ on the left of the equation, is more positive than the equation below it with iodide. So the Fe3+ would be reduced back to Fe2+, or the Fe3+ would be reduced, and the iodide would be oxidized to I2. Now both of these equations can occur, it doesn't matter which way round they occur. If you start with Fe2+, then that equation happens first, and the second one happens second. If you started with Fe3+, it would be the other way round. But the idea is that the value is between that of peroxydisulfate and iodide. The one that wouldn't work is the one at the bottom, the chromium. The reason that one wouldn't work is because yes, it's very negative, yes, it's very likely to be oxidized, or it's the strongest reducing agent in the table, but once you form Cr3+, it's not going to be reduced back because the value is too negative. The reaction to reform Cr2+ is not feasible, so it couldn't act as a catalyst in this case. Again, fairly tricky question there because it's combining two topics together. Question number 30. Which of these species has a shape that's influenced by the presence of one or more lone pairs of electrons? So aluminium chloride, aluminium is in group 3, so it's going to form 3 covalent bonds, 3 bonding pairs, no lone pairs. That one would be trigonal planar. ClF3, that one is influenced by lone pairs, we'll come back to that one in a second. IF6+, if it's a positive ion, that means it's got one less electron, or one fewer electron than normal. So I is in group 7, it's going to have 7 outer electrons. If it's got a positive charge, it's going to have 6 outer electrons. So IF6+ is going to have 6 bonding pairs, no lone pairs. It's going to be octahedral there. PCl6-, if it's got a negative charge, it's got 1 more electron than normal. So PCl6 is going to have 6 bonding pairs with chloride. Phosphorus is in group 5, it normally has 5 outer electrons. because it's got a negative charge, it's got one more electron than normal. So PCl6 minus is going to have 6 bonding pairs, no lone pairs. Again, that one's going to be octahedral. ClF3, chlorine is in group 7. It's got 7 outer electrons. It's formed 3 bonds. So therefore, if it's formed 3 bonds with fluorine, it's going to have 2 lone pairs of electrons left over. It's in group 7. It's formed 3 bonds. Therefore, there's 4 electrons that are not bonded, or 2 lone pairs. 3 bonding pairs, 2 lone pairs would make ClF3 a T-shaped molecule. So in this next question, 31, you've got equal volumes, equal concentrations of different chemicals reacting together. Which one would give the greatest mass of solid? So if you've got barium hydroxide solution and magnesium chloride solution, you're going to be forming barium chloride and magnesium hydroxide. So essentially the ions are going to be switching places. If any one is precipitating out, you're going to be forming a solid. So which one is going to produce the most solid essentially? Barium hydroxide and magnesium sulfate, you're going to form barium sulfate and magnesium hydroxide. Barium hydroxide and sodium chloride, you're going to get sodium hydroxide, and you're going to get barium chloride. And finally, this one you're going to get sodium hydroxide again and barium sulfate. So you need a knowledge of the group 2 solubilities of your sulfate and hydroxide ions. So magnesium hydroxide is a solid. That's the least soluble of the group 2 hydroxides. Barium sulfate is a solid. That's the least soluble of the group 2 sulfates. So barium sulfate is a solid, magnesium hydroxide is a solid. All of the other chemicals that are produced are aqueous. So barium chloride you should know is aqueous. You can get solutions of barium chloride. Sodium hydroxide is aqueous. I'm sure you've dealt with sodium hydroxide solution many times. So which one produces the greatest mass of solid? It's answer B, because both of the products are precipitates. Question 32. This is testing your understanding of pH curves or titration curves. Which indicator should be used in a titration to find the concentration of a solution of methylamine using 0.01 mole per decimeter cubed of hydrochloric acid? So methylamine is a weak base. Hydrochloric acid is a strong acid. So if you were adding the weak base to a strong acid, your pH curve would look like this. You'd start at a low pH, weak base would finish at around pH 9 to 10 depending on the concentration. Your equivalence point is going to be less than 7. It's going to be around 5, pH 5 or so. So which one has an equivalence point or a pH range in an indicator of less than 7? In this case we are looking at answer B. It changes colour in a pH of less than 7 in an alkaline pH, sorry, in an acidic pH is where the equivalence point is. Thymol blue, that's too acidic. It wouldn't change a pH then. These ones would occur, so C and D would occur at higher pHs when you have a strong base, weak acid combination. So your indicator needs to change pH in the vertical section of the pH curve there. So answer B is correct, bromophenol blue. Question 33. Lattice enthalpy values can be obtained from Born-Haber cycles and from calculations based on a perfect ionic model. So Born-Haber cycles are your actual values. Theoretical values assume the ions are perfectly spherical, or it assumes 100% ionic. So the ones that show the greatest percentage difference are the ones that are the least ionic, or have the most covalent character. So which ions are not perfectly spherical out of the options here? So in terms of the most covalent character, the metal and non-metal that are present would have a small cation or a very positive charge. So the smaller the cation, the more positive the charge, the more covalent character you get. You would also have a larger anion. The larger the anion, the more its negative charge overlaps with the positive ion. So small cation, large anion, you get more polarization of the ions, and therefore more covalent character. There's going to be a greater difference between the Born-Haber value and the theoretical value. So out of these compounds here, which one has the greatest difference? Well, cesium is quite a large cation. CS is quite far down in group 1. It's a large cation, it doesn't have much polarization. So they're going to have similar values between the Born-Haber cycle and the theoretical value. Lithium, on the other hand, lithium is a small cation. Fluoride is a small anion, so it doesn't overlap, it doesn't polarize very easily. Iodide is a large anion. So you are going to get quite a bit of covalent character in iodide compounds. So lithium iodide will have the greatest difference between the two. And finally, question 34. Which combination of temperature and pressure would give the greatest equilibrium yield of products? So the forward reaction is endothermic. If the forward reaction is endothermic, to increase the amount of products or to favour the forward reaction, you want to increase the temperature. In terms of pressure, we have 2 moles of gas on the left, we have 3 moles of gas on the right. To favour the side with more moles of gas, you want to reduce the pressure. So increase the temperature, reduce the pressure. That gives us answer C. So that brings us to the end of the 2018 paper 3 multiple choice section. If you'd like any further clarification on any of these questions, please do drop a comment. If there are any other multiple choice questions from any of the other paper 3 series, so 20, 19, 20, etc., then please do check out my other videos. Thanks for watching and good luck with your exams.